Okay. Oh, that's good. Uh-huh. And so, so automatically, what what was that competing theory at the time? That matter was infinitely divisible. That was one competing theory, and then there was another one that started with a pH. What was that one? That there's some phlogiston, yeah, phlogiston theory. So if somebody presented the phlogiston theory to you, what would you say that? What would you say to them that would cause them to rethink their theory? I mean, in other words, what evidence can you give in support of atoms, and that would well, potentially, it depends on what exactly phlogiston is, but if phlogiston is some kind of matter, then those experiments would do what to phlogiston theory? In other words, do you guys know what I'm talking about? Can you visualize what? I know it was just yesterday, but this is why we're going through this exercise today, because I want to just tell you, one of the strategies that I used as a student was I tried to do this review like right after class, because right after class, that's when I remembered the most material. Otherwise, it rapidly disappears. So, as a student, I studied about studying and read some books about it because I wanted to improve. But the book that I read said that 60% of your memory just vanishes the next day. And so if you put that in perspective of time or something, you spend 1 hour, 60% of that hour you just sat through, if you just sit there and not do anything, is gone. So, you might as well just spend like 20 minutes, 10 minutes, 15 minutes rather than, the whole time. And so that's why, to make effective use, to make sure that that time wasn't wasted, if you sit 2 hours in a class, you want to get as much information and retain as much information from that class as possible. But that doesn't always work, because usually if I wait till the next day to review the material, I had forgotten a lot of it and I couldn't really visualize it. So, it's a good idea to do this review afterwards. And what do you want to do in the review? What you want to do in the review is you want to be able to tell somebody, what were the key points that were discussed, from your own words. You want to think about it and formulate it yourself, rather than copying, the professor said this was the key point or that was the key point. You don't want to just be able to memorize those and then spit those out verbatim, but you want to go through the material and then kind of think about it yourself. Now, some of the stuff I didn't make the connection. Some of it I did, but I don't know if I said, those experiments, to me, disprove the phlogiston theory. Why? Well, it depends on what phlogiston is, because when we go back to those experiments here, the other, let me take a side step here, and the other reason for doing it right after is that it gives your mind more time to digest the material and make these neural connections. So the phlogiston theory said all matter that has the ability to burn contains phlogiston. In the process of burning wood, phlogiston is lost and ash remains. And so that seems like the case here. This is not wood, this would be phosphorus, but if we burn the phosphorus, something was lost, the balloon, something was lost, right? But was it really lost? No, it wasn't lost. How do we know it wasn't lost? How do we know nothing was lost here?
Because the weight before and after burning
Yeah, the weight before and after burning is exactly the same, so we didn't lose anything. Right? Nothing, the atoms didn't magically disappear from somewhere, and all of a sudden we had something. It's like gold. If you have a gold coin, you better keep an eye on it continuously, because that gold, all the atoms that make up the gold, or all the phlogiston that makes up the gold, might disappear. And you don't want it to disappear on you, right? Would it? No. I mean, it might disappear. I mean, it might get stolen, or you might lose it, but it's not going to disappear. Right? And so that pretty much debunks the phlogiston theory. So this. And but the other thing is, and this is, phlogiston didn't, that theory didn't say that that matter was infinitely divisible. I just told you about that. That's not in the book here, but the two competing theories were atoms are infinitely divisible matter. But what did Dalton offer as proof? Does this really prove that atoms are the smallest piece of matter that we can have? Or how does this prove, or how does this lead? These are things you want to sort in your mind, because you have to think about it. You have to think that if somebody challenges you on this, like you said, okay, Dalton thought this, and then somebody might ask you, why did Dalton think that? Or you have to think, because this is back in Dalton's time, but this happens all the time today, because science has not died with Dalton. Science continues. And so there are lots of scientists working on trying to discover new things. So if you're working as a scientist in a lab, eventually you're going to have to present your material to whoever. And to that person, these are the types of things you ask yourself. These are the types of things you formulate in your mind, and that is, what evidence do you have in support of atoms? And so what evidence? And so, yeah, these experiments are good evidence, but can you explain to me why these experiments are good evidence? And so you have the point there, and that the point was, as was mentioned, that the atoms that are just rearranged in the process, as we were talking about earlier. And so, but then you go, even if matter was infinitely divisible, can't we rearrange the matter? Let's say, take a little bit of matter here and bring it over there, and then all of a sudden it's different. Can't we do that? And so, a theory has to do two things, right? What does a theory have to do?
It has to predict the law, right?
Well, what was it? It has to protect.
Natural law.
Well, it doesn't really protect the law. It describes it at a fundamental level. In other words, it supports the law. I mean, it supports a detailed description of the law. In other words, it gives a fundamental explanation of the law in that sense. And so the law is the conservation of mass. That is, mass is conserved. And so the atoms here get rearranged, and now we have new arrangements of atoms. So this ash looks totally different than the starting material that we have here. But then if you're a person who's thinking matter can be infinitely divisible, well, that might not be enough. Because if matter were infinitely divisible, we can do the same thing. We can just take different proportions of that matter and then mix them up and then come up with the same thing here. And so one thing that really kind of sealed this is what it predicted. What did Dalton's atomic theory predict? The law of multiple proportions. And so can you give me a little brief rundown? What is the law of multiple proportions?
That the atoms can only rearrange in whole number ratios.
Yeah, that the atoms can only rearrange in whole number ratios. Good. And then that pretty much seals it, because if it were infinitely divisible, then we'd expect to see lots of different ratios of hydrogen to oxygen, rather than just two. We only have two ratios, H2O and H2O2, right? Or carbon and oxygen. We'd expect lots of ratios of carbon and oxygen, but we only see two: carbon dioxide, which is CO2, and carbon monoxide, which is CO. Did I talk about that earlier? Sometimes we see lots of different whole number ratios. Like, for example, when you burn nitrogen in air, is nitrogen easy to burn? No. Nitrogen is very difficult to burn, but it can be burnt in automobile engines. The reason it can be burnt in automobile engines is because, there's very high pressures and very high temperatures in what they call the combustion chamber of an automobile engine. So you can actually burn some nitrogen. When you burn nitrogen in air, you form NOx. Have you heard it? When you go for a smog check, if you have a car, they're going to do an emissions test in which they're going to measure the NOx. NOx. Now, it depends on how intensely you burn it. If stuff is burnt very intensely, then you can form NO2, nitrogen dioxide. Okay? But if it's burned less intensely, it could form NO, which we call nitrogen monoxide or nitric oxide, or not as intense, it can form N2O. N2O is what we call dinitrogen monoxide or nitrous oxide, or laughing gas. So these are different oxides of nitrogen that can form. But with NOx, would you expect it to contain something like NO2.01386, something like that? No, because we aren't going to have fractions. Whereas if matter were infinitely divisible, of course we could expect any little amount we want of oxygen. Just take a little bit of oxygen here, add it there. And so that pretty much sealed it. So that's good. And so the scientific method, that was from the day one. And so now it's already day 3. Do you have the scientific method down? What is it? What are the steps of the scientific method? Observation, patterns, hypothesis, theory. Good. And so that means, since that was on day 1, by the time the midterm comes, that's easy. You don't even have to give it a second thought because you just review it, For me, I'd review my notes. Like, since it's the beginning of the semester, I review my notes every day. There's not many pages of notes to review, but you just review it. And just by reading your notes, then it's going to stick in your mind a lot better. Not only will it stick in your mind a lot better, you're going to get it into your subconscious. When you get it into your subconscious, then you can think of new ways of connecting that knowledge, that newly learned knowledge. A lot of people, what they do is they just cram the information in. When they cram the information in, they really can't come up with new ways of connecting knowledge, and all they can do is kind of regurgitate existing But when did I tell you about the my memory is not so great. This is why I have to do this review all the time. But did I tell you about the time I was in Ralph's after the final exam? Yeah, you also want to do this early. You want to do this early because sometimes it takes time to build these connections. So have you ever been asked a question and you have the answer at the tip of your tongue? It's like there, but it's not there, right? It's close. You think your subconscious is close to coming up with an answer. Well, that happened to me. I was taking a final at UCLA, and the finals there at UCLA are not meant to be finished. So there's some questions you don't get to because the exams are so long, right? But there's one question that I got to, but I couldn't figure out the answer, and it stumped me. But I thought, boy, the answer's almost there. I just had that feeling, but time ran out. As the time ran out, then after the final, I went to Ralph's, which is not so far away, to get some food. And when I was standing in the checkout line, it was like, I think it was like 15 or 20 minutes after I'd left, because it was right there across the street. The answer came to me, and I thought, if I only had like 15 or 20 minutes, I would have had that question. And so, but it was one of those things, the more time you give, the more you can apply this knowledge. And so, certain things, like for example, these experiments. I don't know what the take-home message was here, but then maybe we could apply this to Dalton's. We could apply this to the law of multiple proportions, this kind of stuff. Because when we look at this is going to be a compound of phosphorus and oxygen. I already know what this compound is because I've done this experiment before, burning phosphorus. But I'm sure you probably do too. It's going to be phosphorus and oxygen in some whole number ratio. That's what it is. And the whole number ratio, what we form here is P2O5 or P4O10. Actually, both of these are the same. We'll talk more about these later. This is the simplest, what we call the simplest whole number ratio. This is the actual molecules. The actual molecules like this look like little balls, you know, and they have 4 phosphorus and 10 oxygen atoms all clustered into a cage. These cage molecules are really were really a source of intense study at UCLA. There was a guy there, Professor Fred Hawthorne. You know, I forgot his license plate. His license plate read something like Mr. Boron or Boron Cage or something like this. He was looking at making these cage structures, you know, out of boron and other elements. And what he wanted was he wanted to build these cage molecules and then put certain other atoms on the surface of the cage, atoms that were more attracted to tumor cells versus healthy cells. And so if he built these cages so that they cluster on tumor cells versus healthy cells, then these cages weren't very strong. Then he'd blast the cages with a certain wavelength of light. This wavelength of light was like the resonant frequency for that bond, and that bond would shake like the bridge. Do you know did I show the bridge video? And then that bond would break. And what he wanted to do was he wanted to put a radioactive atom inside there. And so this would be targeting. This is like a little cell bomb that would target tumorous cells. And then it opened the cage, and then that would cause severe damage to the particular cell. And so research along those lines is still going on there. But we'll continue with this. All right, what else? What else were some important points that you want to remember? Yesterday.
States of matter.
States of matter? Right. What were the states of matter that we discussed? Solid, liquid, gas, and plasma. And so plasma, the classic example of plasma is the sun. Can you give me another example of plasma?
Lightning.
Lightning is plasma. Fire is a plasma. And these fluorescent lamps, those have plasma in there. And so flames. And then we talked about something related to the states of matter, and that was temperature. So tell me about temperature. What is temperature all about?
Slower vibrations and faster vibrations.
Mm-hmm. Slower vibrations and faster vibrations, exactly that. Is it just vibrations, or could there be other motion? Yeah, rotations and translations. So we got vibrations, rotations, and translations. Is there anything else? Let's see, that's 3. Is there a fourth? Fourth, motion. We got vibration, rotation, translation. Was there a fourth? No. Yeah, there is no fourth. There are only 3 types of motion. Right? And those 3 types of motion, it's not always free. This is why in the video they're talking about, you know, degrees of freedom and some stuff like that. Degrees of freedom, this is all about geometry and motion and being constricted versus being free, you know, and so only certain types of vibrations are allowed. Those vibrations, you don't have to know this, you know, but does anybody recall how many vibrations? Yeah, for water, 3 vibrations. This is when molecules vibrate and when atoms vibrate, and this is something that I don't think was totally accurate in the video. It was a nice video because it explains things, but in microwave radiation is usually enough to rotate, cause rotations. But we need a little bit more punch in the radiation to cause vibrations, and so usually infrared. You know, have you seen infrared heat lamps? Infrared heat lamps cause vibrations like that. And so it turns out the vibrational frequencies in water are in the infrared, not in the microwave. The rotationals are in the microwave. The microwave operates at 2.4 gigahertz. We're going to talk about radiation, like microwaves, infrared, light. That's all radiation. We're going to talk about that later. Okay. But anyway, temperature is related to motion, and what do we call that? That's given a name. You know, temperature is related to motion, and that is kinetic. Yeah, kinetic molecular theory. Right. Kinetic means motion. Yeah, molecules are molecules. Okay. Kinetic molecular theory. And so the hotter it is, the faster things are moving, both vibrational, or actually with all three, vibrational, translational, and rotational. Or is it all three? You know, does matter have all three? Is it free to move in all three? Well, it depends on what type of matter. So do you know?
You showed us the video about the ice crystals, and
Yeah.
if you try to rotate one of the molecules, it would break the bond, so
Yeah.
it would, like, move that way.
Yeah, and so ice does not have rotational motion. Somebody asked me, there are some solids that do have rotational motion. Did I talk about that?
No.
Okay. There's one solid in particular, it has, it's not really, it's a solid, but methane gas is trapped in pores of the solid. So in the pores of the solid, you have a methane molecule that can spin around. And you can see that using radiation. But ice does not have rotational, nor does ice have what? Translational. In fact, all solids, when we categorize solids only have vibrational. How about liquids? Liquids have all three, and gases have all three available. Now, it depends on the shape of the molecule. If you have a basketball or something like that and it rotates, then you know the energy, it's always rotating. And so that we don't really think of rotational motion for a basketball because it's not like a water molecule. A water molecule is like a boomerang, and so that thing's going to have weird rotations. In fact, that's going to have certain restrictions on the rotations of that as well. So we could see those. And so the molecule has to have some odd shape in order to really see it. If it's just spherical in shape, it doesn't really show differences in rotational motion.
What about plasma? What kind of motion is it?
Plasma has all three types of motion available. Translational, vibrational, and rotational. And so it goes like this. Can you stop the motion? Is it possible to stop the motion?
Yeah.
How?
Lowering the temperature.
Lowering the temperature to what temperature? 0 Kelvin. 0 Kelvin is also equivalent to about how much degrees C or how much in Fahrenheit?
Negative 272
-273
C.
Celsius. Here you could say degrees Celsius, or about what, 464, -464 Fahrenheit. And so you could freeze out the motion at that temperature. So as you warm up a solid, you get more and more motion. Eventually you're going to break the particles free. When you break the particles free, you create a liquid because now the particles can translate, right? As you continue heating it up, pretty soon, you know, in the liquid, the particles are stuck together. Let me ask you this here. So we have the liquid, now we got translational. Here's the solid, this is ice. You recognize the open structure here. Open structures generated to maximize the interactions between the water molecules. The water molecules are nicely arranged here. When the water molecules are nicely arranged like this in a solid, we call it what type of solid? Yeah, crystalline. Versus if they aren't so nicely arranged, like in wax, the molecules in wax are hard to arrange nicely because they flop around too much. And so in wax, we would call that solid more, what was that word? Amorphous. Oh, good. That's good. And so this would be crystalline, nicely arranged. In an amorphous, it would be much more random.
In fact, if you took liquid water like this and froze it, like flash freeze it, if you flash freeze it, you don't give it enough time to crystallize. And so we could make amorphous water by flash freezing this, freezing it so rapidly everything gets stuck in its place here. And then that would be it. And so a lot of people think of amorphous solids as like frozen liquids. You know, liquids are kind of random, not really well ordered. But one thing the liquid has is, what's keeping all the liquid here at the bottom of the container? Is it gravity? You know, yeah, the water is going to go to the bottom of the container because of gravity, but is it going to be held to the bottom of the container by gravity? Or what holds the water molecules together here? Is it gravity? And then by heating it up, we overcome the gravity?
That's the bonds that.
Yeah. It's not gravity that's holding it. You know, because if this were a beaker, this is called a beaker here, it's like a cup. If this beaker were filled with fine flour or something like that, you know, and fine flour is pretty much held down by gravity. And so if you blew on it, like a very finely powdered flour or sugar, if you blew on it, what would happen? It would shoot up and create a big aerosol of flour. You got to watch out for that. But if I blow on the surface of water, you know, water molecule weighs a lot less than a flour molecule. The flour molecules are more, well, actually flour, it's not a molecule, it's structure, so no structure. But if I were to blow on the surface of this, am I going to get a fine aerosol of water? No. And that's because what's holding the water molecules together, they're stuck together. And so the water molecules are really sticky. They like to stick together, and they stick together because of the forces that hold them together. The forces that hold them together we call intermolecular forces. We'll talk about that later, so you don't have to worry about it right now, but essentially these water molecules are quite sticky. Here they've been just stuck together in a solid state. Here we add enough energy to break them free, but not completely free. And so in order to convert this into gas, we need to input a lot of energy to break the water molecules free, and then they can go into the gaseous state here. So, is this where we left off last night? Okay. Did I cover anything else that I missed? What else did I cover?
That's it.
All right. Were there any other important words or concepts that I missed? No? Okay. Good. Yeah, well, that's what you want to be able to make sure that you're doing as well. And so again, I think the things that I found most helpful was to try to write down as much information as possible because it's hard to remember. And two, just review it on a regular basis before the exam, not the night before the exam because that doesn't give you enough time to get into your subconscious, but well before. So you can make applications of it. Okay. Also, the sooner you review, the better, because then you remember things a lot easier. Okay, so we're going to move on here, and so the next thing is, these are examples. So if I take this gas and continue heating it up, that's how you generate plasmas. You take a gas and keep heating it up. And what happens is, when you keep heating it up, they start to move faster and faster. And remember I talked about something? What did I talk about? Atoms. How do we know atoms are the smallest? Like, how do you know an atom is the smallest piece of matter that you can have? I mean, was there evidence that, because if I got something as small as, let's say, a single copper atom, what would happen if you took a single copper atom and tried to smash it would it break up into a whole bunch of littler copper atoms, like mini copper atoms? No, what would happen?
Still be there?
It wouldn't be copper.
It wouldn't be copper. Why not? What would it be?
Particles,
What kind of particles?
electrons, and
Well, yeah, electron. If you haven't heard of electrons, protons, and neutrons, we classify those as subatomic particles, and those subatomic particles don't behave like copper at all. But has anybody ever tried smashing an atom? What did they use to smash atoms? Atom smasher, simply. Have you ever heard of any atom smashers?
The high jump.
The Large Hadron Collider. You should look that up. There's some really interesting videos coming from the Large Hadron. But atom smashers have been around for a long time. There's other names for atom smashers. They call them cyclotrons, synchrotrons, that kind of stuff. So people have, has anybody ever manipulated single atoms before? Yeah. Right? Yeah, nowadays you don't have to be like Dalton. Dalton didn't have much evidence. All Dalton had was conservation of mass and prediction of the law of multiple proportions, which people confirmed, right? Hasn't really been violated. But nowadays we have got plenty of evidence, right? You should be able to name off.
The atomic bombs still split atoms?
Yeah, well, atomic bombs, yeah, that splits atoms for sure. In fact,
Do they still do that?
they still do that. Yeah, nuclear reactors that split atoms. There are two types. There's nuclear reactors that atoms split. They split naturally because we call those atoms. Do you remember what I called those atoms that were unstable?
Radioactive.
And what happens is that a part of the atom, in fact, in the middle of the atom is something called the nucleus, and that nucleus is unstable, and the nucleus breaks apart into smaller nuclei. But you think, okay, if you can split atoms, then you should surely be able to do what the alchemists tried to do. What was the goal of the alchemists? Change lead into gold. So if you got radioactive atoms, then it surely must be possible to change lead into gold, because, right? But it's not. There's no pathway that does that directly. Otherwise, people would be doing that all the time. And so, those are little points here and there. But those little points, it depends. Little points like the atom smasher and this kind of stuff. That's not in the book. But if you knew that, then it's kind of nice, and it's not hard to know, because if you have it written down in your notes, it takes you how long? 10 seconds to read, as far as a review, and then think about how much more knowledge you're going to have going into the test. And the more knowledge you have, the more connections you can make, and the more questions you can answer. And so this got actually this whole thing evolved from this. When I like I said, when I transferred to UCLA, I had to rethink how I studied, and so this is why I ended up reading study books, even though I didn't have that much time to read study books. But I needed to do something to figure out how better to use my time. Because I was already studying the maximum amount of time, and it wasn't showing, even though I was spending every minute of my free time studying. The grades weren't showing. And so that's why I rethought everything. And one of the things I noticed is this. There are people who won't let anything slide. If the professor said this, they knew it. How do they know it? Well, they would try to bring a recorder into class. So this is something I also tried to do. And then they made sure, because obviously they couldn't write as fast as the professor could talk. Sometimes the professor talks, and doesn't write anything on the board. And, there's a lot of information, so a lot of it you might go, oh, that's not important, that's not important, that's not important. But this student knew everything. They knew, and I thought, wow, that's pretty impressive. But the problem is when it came time for the test, they would set the curve. If they set the curve, this student knows everything, and they set the curve like this, then that means I'm still here, but the curve is just shifted. I got it. I have to shift with the curve. And so all of a sudden, well, if that student, because that student has a dream, the student had a dream of becoming a surgeon since kindergarten or something. They're going to do anything it takes. They want the top grade in the class, and they'll do anything it takes to get into UCLA medical school or whatever else their goal was. I forgot exactly. I mean, there are a lot of people. I had a lot of friends, because of being a chemistry major, I had a lot of friends who were interested in medical school. Some of them successful, some of them not successful. But the successful ones, you know, they were on top of it. You know, you might think, not important. No, they were on it. They knew it. You know, and so I changed anyway. Which brings up another story. This student ended up being successful, but it took a long time, because I wasn't planning to go to medical school, but my friend was. So my friend, he's a biology major, so he came to me. You know, he's about to take the MCAT, which is kind of the medical school entrance exam. And so he knows I'm a chemistry major, so he came up to me and said, "Hey, can you help me, you know, review some chemistry?" So I said, "Sure, I'll help you." This is during the quarter. And so we sat down and started reviewing it, and then I realized he forgot everything. It was like starting with a completely blank sheet. You know, he didn't remember a single thing. And it makes sense he didn't remember a single thing, because he took Chem. You know, it was like, what was it? He took Chem. It was probably 2 years or 2.5 years since he took chemistry, and he forgot it all. And so we started, and after about 10 minutes, there's no way you're going to take the MCAT this time around. And he didn't. I mean, there's too much he forgot. And so what he did is he took a year off to study for the MCAT. He took the year off. He didn't pass that first time. And then he took, pass meaning he didn't get into medical school. And then it took him 5 years of review to relearn everything. Although he was working, you know, he got some odd jobs here and there. It took him 5 years to review everything, because he forgot everything. And then I thought, boy, it's so easy to forget. You know, 5 years ago, do you remember everything? I don't remember a thing, you know, not unless I review it. And so if you're planning to do an MCAT or something like that, you know, you don't stop at the end of the semester. I mean, you continue to review all throughout. And reviewing for this guy was, he's going to reread the book. He's going to reread the book. It's 16, whatever it was, I forgot how many pages, 1,200 pages. You're going to reread the book? Really? Well, anyway, that was quite a learning. And so after that, I thought, okay, that's just kind of validated. I mean, I was studying totally different than the way he was studying, and I wouldn't have let it slide that far. But the other guy, anyway. So continuing on here, let's go on with this. The example of the change, let's say if we go from a solid to a liquid to a gas, or a gas to a liquid to a solid. You know, solid to liquid is melting, liquid to gas is boiling. Do you know the reverse? If we go from gas to liquid, what's that called? Condensation. And then liquid to solid is called? So take liquid water and freeze it. It'd be called freezing. Sublimation is when you go directly from a gas to a solid. That would be sublimation. Gas to solid. But those are all examples of physical change, because no matter if it's gaseous water, liquid water, or solid water, it's still water. And so if we change from one form to the other, we didn't change its chemical identity. That is, the formula still stays H2O, regardless. And so all physical changes are associated with no change in chemical identity. And the physical properties would be melting, boiling, melting point, boiling point, freezing point, you know, that kind of stuff. Whereas in a chemical change, we have a change in chemical identity. So, for example, if you burn wood, you no longer have wood left over. You have something else. So the atoms get rearranged and we form new chemical compounds. Compounds are two or more elements combined. Like carbon dioxide would be a compound, water would be a compound, whereas oxygen would be an element. We'll talk about compounds and elements shortly. But anyway, things get rearranged and we have the chemical identity changing, that would be a chemical property. Chemical property are also known as chemical reactions. So if something's flammable, that would be a chemical property. And so we should be able to identify chemical properties and physical properties, or chemical changes and physical changes. And so let's just take a look. The organization of this is wrong. It should be, I don't know why they did it this way. It should be physical properties and physical changes. It should be chemical properties and chemical changes, but they have it flipped. And so it's not physical properties and chemical change, it's physical properties and chemical properties here. Now, this is similar to, remember the dictionary definition? What didn't I like about the dictionary definition of chemistry? That was 2 days ago.
Oh,
Uh-huh.
it said that there's like a study of how molecules interact with each other, but not everything in the molecule can be.
Okay. Well, close, because that was what I didn't like about the PowerPoint 1. PowerPoint chapter 1 said about molecules. Chemistry was the, let me just bring this back up. But, chemistry is the science that studies how molecules behave. But you're absolutely right. Not everything is made up of molecules. Not everything. So for example, let's look at what things. When I look at matter, for example, CO2. Is CO2 made up of molecules? Yes. And so this is what we call a molecule. The molecule is based on the structure. And so we get, actually maybe I shouldn't start with CO2. Have you seen what a CO2 molecule looks like? Do that here. This is what a CO2 molecule looks like here. The color coding, do you recall what black is usually used for?
Carbon.
Carbon, and red? Oxygen. And this is the color coding scheme. But that's a single molecule of CO2. And so we call this a molecular compound. A compound would be two or more elements that are combined, in this fashion. So CO2. How about this? Do you recognize NaCl? What is that? Sodium chloride, table salt. Table salt does not form molecules. Table salt, this is what we call an ionic compound, or it forms what we call an ionic lattice. And so if we look at the structure of something like sodium chloride, it looks quite a bit different than the structure of CO2. Take a look at that real quick here. This is what it looks like here. So there's a watermark here, but ignore that. But we have the sodiums here, which are the gray ones, and then we have the chlorine atoms here. So we have sodium and chlorine atoms packed together in this structure. How would you describe this structure? It's a solid, yeah. It's crystalline. Do you see it's well ordered versus kind of more random ordered? So this is crystalline. It's a crystalline solid. But the way we describe it is there a unique molecule, like one discrete molecule here that we call, that's a sodium chloride molecule? No. It looks like all these are the same, right? And they are. In fact, this we call a lattice structure, crystalline lattice. So this is what we call an ionic lattice structure. The smallest, this would be a small salt crystal. And we can cut it in half, no problem. We can break it into smaller and smaller pieces. But the smallest piece, which would be one sodium and one chlorine atom, the smallest piece of this is not called a molecule. The smallest piece of this is just called a unit. Sodium chloride. It's called a unit because this extended lattice isn't made up of a whole bunch of these discrete units. Because why did I pick this gray one? I could have picked this gray one, or I could have picked this gray one and have the same unit. Right? Depends on how you end it. Since it's not discrete in that way, we call it lattice. Something similar to CO2 is SiO2. Have you ever heard of Si? It's one Si. Do you know what Si is? SN is tin. So SN is tin. Si is silicon. And we have one silicon atom and two oxygens. This is also called silicon dioxide or quartz. Quartz is one of the favorite minerals for geologists because quartz is, there are two forms of quartz. There's amorphous and crystalline. The crystalline is just called quartz crystal, and it forms really nice crystal structures. So you can see the atoms are nicely arranged in quartz crystal. So this quartz crystal. Okay, if we throw that in X-ray diffractometer it's called. And so we'll just do SiO2 crystal structure. I'm going to go X-ray crystal structure. Get a better image, hopefully. I don't really have the great. Maybe this. Just go with a simple one here then. Be something like this, you know. Although it's hard to see, this is pretty well ordered. If you flatten it out into 2 dimensions, then you can really see the order in this. If we flatten this down into 2 dimensions and then just take a profile of this, it looks like this. It has a nicely ordered pattern arrangement, silicon and oxygens here. Now, this is crystalline quartz. Let's take a look at amorphous quartz and see what the difference is between crystalline and amorphous. So it looks, you see, what happens is that nicely ordered arrangement is distorted. And it's a little bit more random. So we call this quartz glass, we call this quartz crystal. And you can buy both, quartz glass and quartz crystal. I used to use quartz glass a lot, for a lot of different applications. Quartz glass is very nice. Okay. But, so the problem with PowerPoint 1 there is that not everything forms molecules. We have a lot of molecules, but we also have ionic lattices, and we call something like this quartz. We call it a covalent lattice. We'll talk about ionic and covalent later. That's called a covalent lattice. And then we have things that form atoms, like for example, xenon gas. Xenon gas, this just forms single atoms of xenon, you know, moving around. This. You can cool them down. You can cool them down, and eventually they'll liquefy, and you cool them down even more, and eventually it'll solidify. You can get them so cold that you can just take those individual atoms and move those around. And do you remember the? Did you see the xenon? The xenon man, yeah. IBM. Oh, it got so hot in here. All right, so what we're going to do is we're going to take sugar. We'll try to make a plasma out of sugar. You know, maybe we can make a plasma. So taking sugar, this is table sugar, and start heating it. First thing that should happen when we start heating this is it should melt. And then if we continue heating it, it should boil. And then if we continue heating it, it should turn into a plasma. Well, the evaporation part comes with boiling. In that part, the liquid will evaporate to dryness eventually, or boil to dryness. But in this case, it turns out that sugar isn't so stable, especially in air. Sugar burns in air. And so by heating it, you're actually going to start burning it. And so what's going to happen is we heat it. Now, you can melt sugar easily in a vacuum. You know what a vacuum is? There's going to be no oxygen there. There's no air. In fact, what's inside a vacuum? Nothing. Absolutely nothing. Uh-huh.
How do you make fire in a vacuum?
How do you make fire in a vacuum? You aren't. You are not going to make. You can make a fire. Let me take that back. You aren't going to make a fire with sugar, because what do you need in order to burn sugar? Oxygen. And so there's no oxygen in a vacuum. But oxygen is what we call the oxidizer. You can make a fire in a vacuum if you supply the oxidizer. Like in space. How do they make a fire in space? There's no air in space. There's no oxygen in space. How are they going to make a fire? Well, they bring it up with them. They, like in the space shuttle, they have solid rocket fuel and liquid oxygen. And the liquid oxygen, they're carrying up all the oxygen with them so they can make a fire there. Well, you can have it in a vacuum if you put stuff inside, so around it you'll have a vacuum, but you got to have some fuel in there and some oxidizer. Now, the oxidizer doesn't have to be oxygen gas. There's lots of other oxidizers. This chart I showed you earlier, this chart is a list of oxidizers. I don't know if I still have it up here. Let's see, do I have it still here? I think I closed it. Let me bring it back up. We don't need oxygen to burn things. We just need things that behave like oxygen, It's like, okay, let's say you want let's say you want a dog that will bark at burglars, right? And so, do you need a specific dog? Like, oh, okay, I need that dog because that dog will bark at a burglar if somebody tries to burglarize your house or whatever, or something like that. Would you need that specific dog, or any dog that would bark? Any dog, right? Or whatever. And so, do you need oxygen? No, you just need something that behaves like oxygen. Are there other things that behave like oxygen? Yes, there are. And so, like for example, here's, do you see that? Oxygen likes to form molecules as well. And it likes to form molecules with two oxygen atoms, O2. And so O2, this is it. But we don't have to have oxygen. We just need something that behaves like oxygen. What else behaves like oxygen? All these behave like oxygen. That sense. And so, for example, we can burn things in chlorine gas with no oxygen around. The flame's going to look different, but it'll burn. And so you could burn things in the absence of oxygen, totally. And so any of these will work. And some of these you can, like PbO2 is a solid. This is called dichromate. That's also a solid. You can burn things. And so some of the older rocket fuels would have the oxidizer and the fuel together in one. And so you don't need oxygen. You don't need air. We're going to come back to this chart and look at it in much more detail later.
So what's happening is the sugar is just burning. You know, the same thing happens, if you heat it up, it's just gonna burn faster. There's no flame here, but sure, you can get a flame if you want. Just heat it up very high, very quick, and you'll get a flame. It's called plasma. But here, you can see, now, is this a physical change or chemical change that's going through? This is a chemical change, you know, because this black carbon deposit is no longer going to taste like sugar, it's not going to behave like sugar, it's not going to be sugar. It forms black carbon deposits and water. Hence its name. You know, table sugar is sucrose, and sucrose is an organic chemical that's in a class of organic chemicals called the carbohydrates. And carbohydrates, the name carbo from carbon and hydrate from water. And so if we look at the formula for sucrose, the formula would be, you know, what atoms is it made out of? 12 carbon, 22 hydrogens, and 11 oxygens. And so it's made up of carbon, hydrogen, and oxygen. And that's it. We could see what the molecules, this is a molecular solid, we could see what molecules of sugar look like if we just search it here. I think I still have it up. I was looking at it earlier. These are different structures, just sucrose. Something like this. Yeah. Okay, that would be a molecule of sucrose there. It's called a carbohydrate because it consists of carbon, and take a look at the hydrogen to oxygen ratio. What is the hydrogen to oxygen ratio? 2 to 1, just like water. H2O. However, do you see any water in sucrose? I don't see any water. Remember, oxygens are red. Actually, these aren't bonded together, but I see carbon, oxygen, carbon. I see hydrogen, oxygen. If this were hydrogen, oxygen, hydrogen, that would be water, but this is a hydrogen, oxygen, carbon. That's not water. And so there's no water in here, but they still call it a carbohydrate because of the 2 to 1 ratio here. This is sucrose here. All carbohydrates have this ratio. So for example, there's another sugar, glucose. If I look at glucose, which is also a carbohydrate, glucose has the formula C6H12O6. Did I get that formula right? C6H12O6. What's the hydrogen to oxygen ratio here? 2 to 1. And so that's the origin carbohydrate. So I end up forming, when this decomposes here, this is what we call a chemical change or chemical process, decomposes into carbon and water. But we didn't have any carbon and water starting off. If we had carbon and water here and we were left with carbon and water here, it would be a physical change. But we started with sucrose here and we end up with carbon and water. This is going to be a chemical change. Chemical change is a chemical property. Well, sugar burns in air. And the same thing with paper. You know, if you have some really old sheets of white paper, it looks like it's burnt a little bit. Or if you take some paper and put it in the oven, you can brown it like sugar. You know, eventually it'll turn black. It'll be carbon. Let's move on here. All right, when we look at matter, you know, one of the things we'd like to know is this. When I look at some matter like this, is this pure water or is this impure water? Pure water? Yeah? So would you drink this water if I gave it to you? Why not? If it's pure water, if you're thirsty, you might as well drink it. Well, that's a good question, isn't that? Because that's what you want to know. Is it pure matter that we're dealing with or mixture?
And so this a question we always ask when we're looking at matter. Like this blue liquid, is this blue liquid pure or a mixture? Yeah, this one's going to be a mixture. And so first thing is we're just going to define it. Pure substance or pure piece of matter is going to have a fixed composition and fixed properties. Whereas mixtures, because mixtures, we can have variable composition. We can mix it in different ratios. Depends on the ratio we mix it. Like for example, I could make a mixture here. I could just add some sugar to the water. I'll get sugar water. And if I told you this is pure sugar water, maybe that's okay. This is pure sugar water, but technically, if it's difficult because if I say I'm going to sell you some pure sugar water, what are you buying? You're buying a mixture, and then you think, well, it's pure, so just get it. But you might bring it home and it just tastes like water. They said it's pure sugar water, but they probably ended up adding, let's say, a minute amount of sugar to the water, and you were expecting something very sweet because you're thinking it's sugar water, it should be sweet. But then you go back and complain, hey, this isn't pure, I don't taste any sugar in this water. And they said, it's pure, I just added a little bit of sugar to the water. You have a case against them? No, you don't have a case against them because it could very well be pure sugar water, right? But the problem with mixtures is mixtures will have variable composition, therefore variable properties. So when you're buying sugar water from one vendor versus buying sugar water from another vendor, they can be totally different. Whereas if you buy pure water from one vendor versus pure water from another vendor, they better be the same, because pure water should be pure water, right? But sugar water isn't. What about air? I want to bottle it up and I want to call it pure air. I'm going to start selling pure air in polluted cities. Is it possible? Yeah, air is a mixture too. I mean, we could get an air purifier. Somebody said, what if you put it through an air purifier, then isn't it pure? Well, it's been purified, so it's cleaned up. It's still a mixture. The mixture is going to have variable composition. So do you think the air composition here is the same as the air composition, let's say, in other parts of the world? No. It's going to be close. Do you know what the average composition of air is? It should be close, but let's see, where did I put it? Oh, here it is. There's going to be other things here, pollutants and whatnot, like NOx, NOx, maybe some carbon monoxide there, maybe more carbon dioxide. Particulates are a growing concern as well. So there could be other pollutants here. But on average, this is the composition of air. Air is mostly nitrogen, and then oxygen's next. And so this is a rough approximate, around 80% nitrogen, around 20% oxygen. 80-20 ratio. And then some other stuff in the air as well. Xenon, neon, hydrogen, helium, krypton, some carbon dioxide, some argon. Argon's a pretty big component. And so air is a mixture. What happens is this. This is the average composition of air at sea level. It turns out as you get higher and higher in altitude, the composition changes a little bit. At higher elevations, some of the heavier elements, this is due to gravity, some of the heavier elements, the percentage will go down actually at higher elevation. And so at higher elevations, we expect a little bit of decrease in argon's heavy, it's a heavy atom. Oxygen likes to form O2 molecules, and so those are heavier than nitrogen. So we're going to get a little bit, not much, but just a little bit less oxygen. That's called fractionation. fractionation based on interactions with gravity and mass. And so this is the reason why, as you get higher and higher in elevation, we get less and less of the heavier molecules, less and less of the heavier atoms go up. In fact, if we go out in deep in space, we only see very light atoms or light molecules like hydrogen or helium. Not only that, did you know that all oxygen atoms don't weigh the same amount? Did you know that? Maybe I shouldn't mention this yet, but it's kind of weird that some oxygens are heavier than others. In fact, when you had a cup of water today, if you had a cup of water today, you drank some heavier water molecules and some lighter water molecules. Did you know that? Could you taste the difference? It doesn't taste any different. Chemically, they're the same. But it turns out that leads to fractionation. And so if you're looking in the deep oceans, at the bottom of the deep oceans, you should find more of the heavier water molecules or more of the lighter water molecules in the deep ocean. And the heavier water molecules should sink down to the bottom more. And the lighter ones, so on the surface it should be more enriched in the lighter molecules. Well, that happens with ozone as well. It's easy to tell if the ozone came from the ozone layer or if the ozone came from pollution at ground level. Because ozone that comes from pollution at ground level is going to have a lot more of the heavier oxygen atoms versus ozone in the ozone layer. Ozone in the ozone layer will have lighter. And so we'll see that in fractionation. So we'll see compositions vary, in lots of different ways. But this is one of the ways. So water, even though this is pure water, in a way it is kind of like a mixture because there are different water molecules in there. But we'll talk more about that later. That's a topic called isotopes. Actually, not that much later because isotopes are coming right up. But one of the challenges in chemistry is if you're given a mixture, or actually identifying it, like this water, I don't know if this is pure water or not. How would I identify it if this is pure water? Well, analytical chemists are really into that. Analytical chemists want to know, what else is in this water. And they'll try to find what else is in this water, how much. And so water districts often do this. Water districts will send out water samples for analysis by analytical chemists, and then they'll have some water report that they'll publish. Right? But we're always doing this because we want to know, what is that? Is it pure or mixture? If it's a mixture, what's in it? And how much? We'll figure that out. One way to tell if this water is pure or not is, we know some of the properties of pure water, and so we could just measure some of the properties. One of the properties of pure water is it better boil at 100 degrees C. If the water's not boiling at 100 degrees C, then there's no way. Well, I shouldn't say there's no way, because does water boil at 100 degrees C in Denver? Or does water boil at 100 degrees C? I'll talk about it more later. But let's say water should boil at 100 degrees C under normal atmospheric conditions. Because the atmospheric pressure, that is the air pressure, varies day to day. And it depends. If the air pressure is high, then it takes a little bit more energy, a little bit more heat to boil off the water. If the air pressure is low, like up on the high mountains, then it boils a little lower. So if you're in Denver and you're cooking some pasta and the water is boiling at a little lower temperature, then you have to cook it longer, because otherwise it's not going to cook all the way. And so normally at high elevations we need to add time to the cooking to compensate for the lower temperature. It boils out because of lower atmospheric pressure. But anyway, we'll talk about that later. But we know water boils at 100. If it doesn't boil at 100, then it's probably not pure, or we're at some high elevation or Okay, and then let's say this is sugar water. Sugar water boils at a higher temperature than pure water. And then as you start boiling the sugar water, what happens is the sugar stays, but the water gets boiled off or evaporates off. As the water evaporates off, the sugar water becomes more and more concentrated. And the more concentrated it becomes, the harder it is to boil. And so this is what's happening here. As the sugar water becomes more concentrated, it's harder to boil, and the temperature's got to climb in order to boil. And so that's one way we might be able to tell, but sometimes it's hard, you know, so we need to do multiple things to tell if it's a mixture or if it's pure. But one of the things is visually we can't tell really because it looks, you know, when you describe this, it looks very pure. It looks very uniform. That uniformity we call homogeneous. This looks very homogeneous, so it looks pure. The same thing with this blue liquid. This blue liquid looks very pure. Looks very pure. But it's a mixture. Some things are obviously not pure. Some things are obviously a mixture. And so if I look at these 4 beakers, these cups are called beakers, and they're usually glass. All of these look like they're pure here. And we have to analyze this. And so if we had some kind of device that can look at the molecules and make this up, this is what it would look like. You know, this is hard to do. We can't really do this. We'd have to freeze it down, put it in X-rays, or do something else like that. Oh, that's right. It's time for a break. Do you guys want to go for a break now? Or just keep going and end early? Break? Okay. You could go for a short break. Keep going and end a little earlier? All right. Yeah, if you need to take a break first. This looks very homogeneous, as does this. This looks homogeneous, homogeneous, homogeneous. So they all look pure. And so we have to measure some of the properties of this to determine, or we have to analyze this. So if we analyze this, then we say, oh, this one is actually pure, this liquid. It's a brown liquid. It consists of Br2. Br, do you know what element Br is? Bromine. Bromine. And it likes to form these 2-atom molecules. So these it's pure, nothing else, pure bromine. You should recognize this. What is this? Water. This is not pure. This is bromine in water. So you see some bromine water and water molecules, but it looks very homogeneous. It looks very uniform. It looks pure, but it's not. It's a mixture. It's a mixture because we can vary the amount of bromine in there. We can make it concentrated or we can make it dilute. In fact, in the next beaker here, we just add a lot more bromine to make it a lot more concentrated. So this is concentrated bromine water. This is more dilute bromine water. Now, mixtures don't have fixed composition. They have variable composition, and therefore they have variable properties. But when we talk about variable composition and variable properties, this is what I mean. Variable just means if you add more bromine or less bromine, but you know, it doesn't mean that if you make it consistently the same way each time. Let's say you make sugar water and you always add the same amount of sugar to the same amount of water each time. Are you always going to get the same sweetness of water? If you always add the same amount of sugar to the same, it's a mixture. So, but will you always get the same sweetness? Well, actually you should. You know, if it's the same amount of sugar and the same amount of water, you should always get the same properties, right? And so this, if you always mix it to this concentration, the properties of this are fixed, right? What they mean by variable variable properties is because let's say you overshoot it or you undershoot it, it's going to be different. But if you make it the exact same way each time, then it should be the same, even though it's a mixture. Does that make sense? Okay. And so when I say variable composition, I mean that's if you change the composition. But if you leave the composition like the air, you know, if the air is always the same composition, then it's going to have the same properties, even though it's a mixture. And so it would be, but we know that the air here is different than the air in New York, so it's going to have slightly different properties. So continuing on with pure substances and mixtures here. What we just saw are solutions. Solutions are homogeneous mixtures. So those you couldn't really tell if they were mixtures or not because they were solutions. They were homogeneous. Air is a homogeneous mixture. You know, air you can't really tell. And so when something's homogeneous, it has a uniform appearance and uniform properties throughout. Uniform properties means this versus like sand in water. If you tried to mix sand and water, that would be very heterogeneous because the sand would have different properties than the water. So it's very clear. Okay, when we're talking about homogeneous, we're talking about phase. In terms of sand and water would be two phases. One phase would be solid, the other phase would be liquid. The sand would be solid, the water would be liquid. That would be heterogeneous. And so heterogeneous mixtures have multiple phases, and these are easily seen. Whereas homogeneous mixtures have a single phase, therefore they're tricky. Heterogeneous things of a non-uniform appearance. Of a non-uniform. You don't have to write all of this. Let's just apply this here. And so if we take some pure water here, and pure, do you recognize this molecule? This one is, how many carbons? It's actually 2 carbons. How many hydrogens? Let's see. 1, 2, 3, 4. There's some hidden on the other side. Altogether, there's actually 6. Really hard to see. And 1 oxygen. This molecule I recognize right off. You know what this is? This is called ethanol. Ethanol is an alcohol. And if you look at it, it's very homogeneous. It's pure. This is pure ethanol. This is very homogeneous. This is pure water. If we mix ethanol and water, they mix very easily. Ethanol and water, we get ethanol and water mixture. But when we look at the ethanol water mixture, does that look homogeneous or heterogeneous? Homogeneous. This looks pure, but it's not really pure because it has variable composition. In this case, it's fixed here, you know, whatever that is. But if you're given this, you know, if you're given ethanol and water, we have a mixture. And so forming a mixture is easy, just mix them together. But separating a mixture is kind of difficult. So let's say I want to go backwards from this. How would I go backwards? You know, I don't want my mixture anymore. I just want pure water and ethanol. Now they're mixed together. Is there a way I can separate them? The ethanol and the water. You could heat it up, yeah. You could heat it up. In fact, that's what a lot of people do, you know. In fact, a lot of people do that with water. You know, if there's impurities in this water, one way to get rid of the impurities is by distillation. And so if you go and buy distilled water is about as pure as you can get in the supermarket. Because what they do is they heat it up and they boil the water and then capture that. And that should leave any impurities back in the container behind. And so that's distillation. You could do the same thing here. If you heat this up, it turns out that ethanol has a much lower boiling point. Things that have a lower boiling point are called volatile. So ethanol is more volatile. It'll evaporate off the surface more readily than water will. Water is much stickier than ethanol. And so ethanol vaporizes, and then we can capture it. And so what we'll do is we'll put the ethanol water here. You don't want to use an open flame because ethanol has a chemical property. One of the chemical properties of ethanol is very flammable. It burns really easily. And so we use an electric heater here. Use an electric heater and start to boil this. As this boils, the ethanol gets vaporized first. It's not as sticky as water. The ethanol gets vaporized here in the gas state, but we want to capture it.
we aren't going to capture it. We're just going to let it stay hot. If it stays hot, the surfaces are hot, it's not going to condense. And then we pass this by. This is a tube with a jacket around this. This jacket is hollow. So what you can do is you can pump in cold water here. Usually you pump in ice water here around the jacket, which would cool this down. So as the ethanol hits the inside of this tube, it gets cold and condenses back into liquid, and then it drips over here. You should end up with pure ethanol here. And then the same thing they do with water. You know, if you have impure water, you heat it up. Hopefully the impurities, if the impurities come off first, that's fine, let them go up, and then the water will come off. And some impurities are going to have very high melting and very high boiling points, so those stay down here. And that way we can capture the water, we'll have pure liquid water. And so this is distilled water here, which should be high purity. What's higher in purity, distilled water or filtered water? Distilled water. Filtration might not capture all the impurities. Although reverse osmosis is very good though. But there's other filtration methods that aren't as effective. So that's pure. With ethanol, it's a little bit tricky because a little bit of the ethanol gets sucked in here. And so I did this experiment when I was a student. I made ethanol water. Actually, I made ethanol water and a whole bunch of other junk. The experiment, I remember this very well. Took like a 1 gallon jug, glass jug, and then filled it with sugar and water. Just a big glass jug like this, and put some sugar. Sugar, aka what? Sucrose. Some sucrose in here. And then some water, H2O. The sucrose dissolves in water and makes sugar water. And make sugar water, and then add some yeast to my sugar water. You know, I guess you can buy sugar water, but it's easy to make, right? Well, it's hard to make it the same concentration each time. So yeast, and then you put like a balloon on here so you can see how much reaction is taking place, because as the yeast ferments the sugar, it creates CO2. And so you can watch this reaction progress. It's hard to see sometimes. You can watch the reaction progress by the balloon filling up with CO2. And the whole thing's going to weigh the same, you know, before and after, even though you're going to get a balloon filled with CO2. It's just the atoms are being rearranged. But in here, we're going to have ethanol plus other stuff. Well, I don't want that other stuff. You know, I just want the ethanol. And so I want to separate the ethanol, hopefully pure, you know, away from the yeast and other stuff. And so you do is you just take this mixture here and then throw it into, probably filter it. We want to filter out the yeast first. Are you guys familiar with filtration? And so there's probably some solid yeast particles left over. I'll probably filter those out. Usually we use filter paper for that, but the filter paper, you know, the pores aren't too terribly small. But you can buy lots of different filter papers. You know, they have filter papers, they have different ones. They have qualitative filter paper, which has big pores, but the advantage is it filters very fast. And then they have quantitative filter paper, which has small pores, but it's so slow. You know, you pour in some water there, and then you just wait. And wait for an hour, and nothing's happened. It's like the water's just sitting in there. This is just slowly filtering through. You can buy filter papers that are with such tiny pores, nothing goes through them. I mean, it would take days to filter. And those are made out of ceramic and glass. They're called fritted discs. There, what you have to do is you have to seal this and then suck out the air to create if you suck out the air in the container, it'll create a vacuum. And that vacuum will pull the liquid through here and speed up the process. So it's called vacuum filtration. Vacuum filtration is very common. But for yeast, we can just get by with qualitative. We just filter out most of the yeast out of there. And so then but we still got a mixture. You know, did that filtration really purify everything? No. We got a mixture. And then we take that mixture and throw it in the distillation apparatus like this. And then distill it. Well, the problem is this, water's kind of sticky in a way. And so I'd like to get pure ethanol here. We can get pure water here, no problem. We can get pure lots of other liquids here, no problem. But ethanol has a problem with sticking with a little bit of water. And so the purest ethanol you can get is only 95% ethanol. 95% ethanol is what we call 190 proof ethanol. So that's as pure as you can get from distillation. So I wanted to taste what 190 proof alcohol tasted like. So I tasted a little bit of it. It wasn't anything special because what happened was it just evaporated so fast. It's so volatile. It hits your tongue and vaporizes. Kind of thing. And so it wasn't anything special. But still. So how do you get pure ethanol? Well, to get pure ethanol, you're going to have to use other techniques, other separation techniques, which we haven't talked about here. And then you can get 100% or 200 proof alcohol. We have some in the lab here. It's been denatured. So our pure alcohol, they put some chemicals in here to denature it so nobody will drink it, or be tempted to drink it. Those chemicals are harmful here. A little, but they're in very small amounts. This shouldn't affect the reaction. Okay, so when we have mixtures, separations are very important. In fact, some of the separations are very tough. Let's say you have reduced lung capacity. So what you might think air is only 20% oxygen, right? It's not that much oxygen. Maybe you need more oxygen. And so, some people will get more oxygen. They'll buy a cylinder of oxygen, which is close to pure oxygen, and then just breathe that stuff. And I was online and I saw, you can buy this stuff. Have you seen that? Like canned oxygen? Yeah, I saw that recently. I was thinking it was expensive, so I didn't necessarily buy it. But yeah, you can get oxygen. And then I remember, this is research that was happening at UCSB. And how do you get oxygen? Do they make it, or where do they get oxygen from? And so one of the places I used to get oxygen from is called Liquid Air. You ever heard of them? Liquid Air. They have offices all over the U.S. and internationally. But the name Liquid Air should tell you something about their company. You know where they get their oxygen from? Not water. The air. They get the oxygen from air. And so you're going, wow, they're getting the oxygen from air? Air is free. They must be making a killing. But they aren't really making a killing because you know what they have to do? First, they take all that air, and the air's not very dense, then they have to cool down the air. They cool it down until it condenses into a liquid. Well, that's very cold. And so they need all kinds of refrigeration equipment to do that. And so they cool down the air and get a pool of liquid air. Once they have a pool of liquid air, then what do you think they do with it? They distill it. And so as they distill it, the oxygen comes off first, they trap that, and they got the pure oxygen. You can go buy the pure oxygen. Therefore, it's going to be expensive, right? There's all the energy that's involved in that process. So people were looking at maybe easier and less expensive ways of separating out nitrogen from oxygen. And so at UCSB, I was in the materials department, and that was one of the projects that was getting a lot of attention there. The project was to make a filter with pores so small that the oxygens could pass through, but the nitrogens would be blocked. And that filter has molecular or molecule-sized pores, so they call it a molecular sieve, like a flour sieve. Flour sieves, they get rid of the chunks of flour, and you just sieve it through it. It's kind of like a filter, a very porous filter. Well, they have molecular sieves. And so all you have to do here is you don't have to cool down the air to extreme temperatures, like extremely low temperatures. this is it here. See if we have something. Maybe Wikipedia's good. These are a whole bunch of different molecular sieves. You can see the product though. The product is something like this. Now, rather than, let's say you needed extra oxygen, 20% is not enough. You need air that's been enriched. It's not perfect, but you don't have to wheel around an oxygen cylinder around. I remember seeing people wheeling around oxygen cylinders, right? This is very heavy, very cumbersome. Obviously, you aren't going to be very mobile. But now with these molecular sieves, all they do is they have a little filter in there and a pump, and they'll just pump the air through the filter, and it filters out most. It's not perfect. You aren't going to get 100% oxygen, but you're definitely going to get more than 20% oxygen, a lot more than 20% oxygen, because most of the nitrogen gets filtered out. So this would be a molecular sieve here system. So mixtures and separating mixtures is very important in science, and sometimes it's not so easy to do. In fact, a lot of times it's not so easy to do. Sometimes it's not so hard to do. And so if we take a look at this here, this doesn't look so hard to do. I wouldn't want to do it because it seems like a pain. And then how often do you work with this mixture? This is a mixture of this yellow stuff. This yellow stuff is sulfur. It's pure sulfur. And these are iron filings. And so iron is magnetic, sulfur is not. And so you can separate the sulfur from the iron. This. Yeah. There are lots of different separation techniques, like dissolving, etc. So we look at those. We talk about distillation. Here. We talk about this word volatile. The more volatile stuff will boil off first. Talk about filtration. Lots of different sizes of filters based on particle size. This is distillation apparatus. Let me show you one that you've probably seen. You've probably seen this. This is industrial size distiller. And so all the oil refineries, they'll put crude oil. Crude oil is a mixture, and then they'll heat it up. And so the smaller molecules are going to rise to the top. The heavier molecules are going to stay at the bottom. The smaller molecules, they can capture capture different fractions. It also depends on temperature. They can ramp up the temperature. So low temperature, the smaller, more volatile molecules rise, and the other ones stay. This is the operation. Okay. This is distillation. It's filtration. Okay. I drank this stuff, but you shouldn't always trust people. Trust people who make their own alcohol. You shouldn't trust them, because you might not have heard these stories, but I hear them quite a lot being a chemist. Do you know people try to ferment? I'm fermenting sugar. You can ferment grain. Grain will do the same thing, give you ethanol. But some people, they don't want to. Grain is expensive. Sugar is expensive. So they try fermenting other stuff, like paper. Paper? So, it kind of makes sense. If you ferment paper, you know what paper is made out of? cellulose fiber. Do you know what cellulose is made of? Glucose. This is why termites love paper and they love wood. In fact, wood, do you know wood is made out of cellulose? Cellulose is made out of glucose. Glucose is a carbohydrate, so why don't I just use wood? Wood containing glucose, carbohydrate, and ferment alcohol. And so, so people do this. It's called wood alcohol versus grain alcohol. Ethanol is grain alcohol. Paper or wood is wood alcohol. What's the difference between wood alcohol and grain alcohol? Even though they're both starting off with essentially sugar, although we can't eat this, termites eat this and they love this stuff, right? We can't eat it because we don't have the enzymes to digest it. But if you use here wood instead, thinking that wood has glucose, which it is, it's made up of entirely, cellulose is made up entirely of glucose molecules stuck together. But they're stuck together in a different way. This is why three-dimensional structure is so important in chemistry. You always want to know this three-dimensional structure. Because, have you heard of glycogen? Glycogen, the glucose molecules are bonded like this. Glucose, the glucose molecules are bonded like this to one another. Just that difference in bonding means that we can eat one, but we can't eat the other. And so termites can't eat sugar because they won't be able to digest it, even though it's made up of the same stuff. But anyway, wood alcohol does not lead to ethanol. Ethanol is 2 carbons. Wood alcohol leads to methanol. Methanol, okay, is this versus ethanol. Ethanol has 2 carbons and it has this formula. So ethanol is okay. Of course, you don't want to drink too much of it, but in moderation it's okay. Methanol is no good. This stuff is very toxic. And so I think it was last year or the year before I read a story, like 22 people died from drinking methanol in one gathering. And the sad thing is, a lot of the people paid for the methanol. They paid somebody for the alcohol to drink. The people that didn't die ended up going blind, and then you go, oh, going blind, that sounds like some urban tale, but it's not. Because methanol, when it's metabolized in your system, forms formic acid or methanoic acid, which attacks your optical nerves. And I guess it's irreversible because they went permanently blind. And it's been well known. And so watch out for that. And so, well, the properties of methanol and the properties of ethanol are going to be totally different. So you shouldn't be able to get those mixed up, but they look exactly the same. I mean, they're both clear, colorless liquids, right? And so let's just, I had that article. It's hard to find wood alcohol death. Well, the story, it doesn't really come up because these wood alcohol deaths don't get that much press, but in the chemistry journals, they do get a lot of press. So the 22 deaths that happened recently, that wasn't that long ago. It's like 1 or 2 years ago. But here's one in 2012, Prague. Let's look at that. 2012, Prague, allow. That's probably one. This is from Smithsonian. Oh, this is knockoff industry. So there's knockoff booze from bootleggers, cheaply produced alcohol. Cheaply produced wood is a lot cheaper than sugar, right? So cheaply produced alcohol that can be contaminated with methanol or is largely methanol. So how many? 20 deaths. Methanol poisoning is a dreadful way to go. Even if you manage to avoid death, blindness and brain damage are common in survivors, hence the term blind drunk. Last winter, illegally made liquor killed at least 169 people in India. In Estonia, in 2001, 111 people were affected by a bad batch of alcohol. So that's pretty nasty. And so obviously we're very concerned about purity, we're very concerned about mixers, we're very concerned about, you know, properties and composition and knowing what, you know, what we have here. As far as that goes. So yeah, I drank this stuff myself because I made it and I trust it. I think I trust my lab technique and my understanding of chemistry and that. But that doesn't necessarily mean I trust anybody else, especially with homemade stuff. Because you know, somebody might think, oh, you know, it's well known that paper is made up of, you know, glucose molecules just bonded in a funny way. Okay, let's get back to this. I'm going to end pretty soon for minutes. So we're always interested, you know, what the impurities are. Is it pure? If it's pure, what is it? And so if we have something that's pure, then we got to figure out what it is. And if we have a pure substance, it could be one of two things. It could be an element, like pure gold or whatever else. Or if it's pure, it could be a compound. Like we could have pure sugar, you know, pure sucrose. Could we have pure sterling silver? We could have pure silver, but could we have pure sterling silver? Or could we have pure 18 karat gold? Is 18 karat gold pure or a mixture?
Pure.
How about what's 24 karat gold? Is 24 karat gold pure or mixture? Yeah, 18 karat's a mixture. Depends on who mixed it up, you know, who made it. You know, if I were making 18 karat, you know, you'd probably want to make it with lots of gold, or you might want to make it with minimal gold. It depends on what the standards are. But anyway, different people have different standards, so you gotta watch out. But compounds are always going to have the same ratio. So if I was looking at like 18 karat gold, it's a mixture, and it's not always going to have the same ratio. It depends on who made it. It's like sugar water. If you ask 3 people to make sugar water, they're probably going to get 3 different compositions of sugar water. Just like if you ask 3 people to make 18 karat gold, they're probably going to get 3 different compositions of 18 karat gold. They're all going to be close, I'm sure. Otherwise, somebody will say, I'm being cheated, you know, not enough gold. Or I got lucky, I got lots of gold, you know, something like that. But if you got pure sucrose, then everybody's going to have the same. It's going to be 100% sucrose. You can't have anything else in there. It's going to be just pure sugar. If you have pure paper, you might go, oh, pure paper, it's pure cellulose. Pure cellulose, it's pure glucose. Glucose linked together in a funny way. And it would be pure cellulose. Okay. Now, those are compounds, you know, and we're going to have the 2 types of things. So when we're looking at matter, like this, we look at matter. Is it homogeneous? Or is it heterogeneous? Oh, sorry, it's fairly hard to see. I'll finish off with this. Is it homogeneous matter or is it heterogeneous matter? If it's heterogeneous, it's got to be a mixture. If it's homogeneous, it could be pure or it could be a mixture. It's hard to tell. And so if it's pure, then we have 2 choices. If it's pure, that means it's either like pure gold or pure oxygen or pure element. And so it could be an element. Or it could be like pure sugar or pure water. Water would be a compound. And so that means it's either an element or a compound. It can't be both because then it would be a mixture. But if it's homogeneous, it also might be a mixture, a homogeneous mixture in this case. And so both of these mixtures can be separated into pure substances. And mixtures can all be separated by physical means. That is, we can use physical separation techniques. To do that. Now compounds are going to be two or more elements, but the ratio is fixed. And the way we can separate, let's say we have water, and I want to separate hydrogen from oxygen in water. Can I do that by filtration? Even if I use a small filter, can I get a molecular sieve or atomic sieve and just push the water through and then separate the oxygen from the hydrogen? That'd be pretty good, because then if you got a hydrogen-powered car or something, you can start. No. Could I do it by distillation? No. In fact, there's no physical means of separating the hydrogen from the oxygen. The only way I can separate the hydrogen from the oxygen in a compound is by chemical separation techniques. And then I can separate it into the elements, hydrogen and oxygen. You know, one chemical separation technique that's used for water is electrolysis. If you run electricity through water, like a little lightning bolt through water, then it'll break up the water molecules, and it could form hydrogen and oxygen in there. And so and I'll set it up. We're gonna do that. It's very easy to do. And people are looking at using solar energy to electrolyze water to form hydrogen for hydrogen-powered vehicles, and that kind of stuff, to build a hydrogen economy. Okay. All right, I'll stop here, and then we're going to finish up the chapter. And do you have any questions? Yeah. Homework, though, I'm going to post the homework on Piazza. I'll probably assign some homework problems for chapter 2. So why don't you take a look at that? Give me a chance. But right now, for homework, what you should do is review. Review your notes, make sure they're complete, and you can use those for study. Or if you like writing your own notes, you should write your own notes.